Okay, in this video we're going to be looking again at limits, but this time limits involving infinity. Both the limit as x approaches infinity, as y approaches a constant, and as x approaches a constant, and y approaches infinity. We've called these before by the names of horizontal asymptote, which is the first one, the limit as x approaches infinity, y approaches a constant, and vertical asymptote, which is as x approaches a constant, y approaches infinity. And infinity, believe it or not, could be positive or negative. So that's pretty important that you distinguish between the two. So in this first one, looking at it in terms of horizontal asymptote, by definition of a limit, okay, looking at it here, you know it's a horizontal asymptote if the limit as x approaches infinity and the limit as x approaches negative infinity are equivalent. So they're equal to the same y value. Okay, so as basically, as x approaches infinity, y approaches a constant value. Now, if you look, what would a regular horizontal asymptote look like? Well, think of a function like e or something like that, an exponential function. Okay, e approaches this blue line but never ever actually gets there. Okay, you could also have, well, what if I have 1 over x or something similar to that? Then this isn't 1 over x, I know, but it's this function, okay? There's a horizontal asymptote here at this value of y equals b. So horizontal asymptotes can look like lots of things. Let's look at an example here. Use graphs and tables to find the limit as x approaches infinity, negative infinity, and then identify the horizontal asymptotes, because there could be more than one. If these are not the same, okay, then there's more than one horizontal asymptote happening. So go ahead and graph this, try to answer those questions, and then come back and check your answers. Okay, if you graphed it, your graph should look something like this. Let me find it here. Hold on. There it goes. Okay, whatever it looks like, you notice as also you could look at the table of values, plug in really large numbers for x, really small numbers for x. If you need help doing that, just ask me in class, because that's pretty important to be able to find those horizontal asymptotes algebraically and using tables. But if you look at the graph, looking at it graphically, you can see that to the left and to the right goes all the way out to infinity and has that horizontal asymptote right here at 1. Okay, so the left and the right are the same. So on A, the limit as it approaches positive infinity is equal to 1, and the limit as it approaches negative infinity is equal to 1. And so C, there's only one horizontal asymptote, and that's y equals 1. And so when it asks you for a horizontal asymptote, that's a y equals equation. Okay, so make sure you write that in terms of an equation. And there's more properties. These properties should look familiar. We're not even close to being done with these. Again, I just put them in there for you. If it looks like a duck, walks like a duck, talks like a duck, then it's probably a duck. Basic properties of mathematics come into are applied here. Okay, now infinite limits the other way around. As x approaches some value, so a is a constant value. All right, so if a is your constant, oh, look at that perfect vertical line there. Okay, so let's sketch a little graph. Approaches a constant value. Let's say this red line represents x equals a, some value. And as your function approaches it, now look, your function can either go in the positive infinity direction or your function can go into the negative infinity direction. And now here's the tricky part. That's coming from the left. So it's the limit as x approaches a from the left. Okay, so it can be positive or negative infinity. Also, you have the same thing that could be happening on the right side, going towards infinity and going towards negative infinity. So you could have a right-handed limit, so that's x approaches a from the right. That could be both positive and or negative infinity. Chances are most likely that it's not both. It's one or the other from the left and then one or the other from the right. But in the rare cases, I'm guessing it could be. So here's your definition in terms of a limit. Just be familiar with that in terms of a limit of a vertical asymptote. And again, equations for vertical asymptotes are x equals. So don't just write a value, write an equation. Look at this first one. Okay, looking at this, you can simplify this one, by taking this and multiplying it over and whatnot, but we're not necessarily going to do that. We're going to do this two different ways. Number one, we're going to try to do it algebraically. By try, I mean you're going to try it on your own, and then you're going to come back to the video and see if you're right. And then you're going to check your answer graphically. So look at the graph and see if you get the same answer. So let's try to do this algebraically. If you need a little hint, here's your hint. If you don't, get started. If you need a little hint, come back and get the hint. Okay, here's my hint. We're going to go ahead and plug. We're going to start with positive infinity. The limit as x approaches positive infinity. We're going to go ahead and plug that in. Now, when you get a value, let's say a over infinity, what that means is you have some constant over the value of infinity. So some small number over an extremely large number. Do that in your calculator. Take 3 divided by 100 million. Okay, what value is it really close to? 0. So as x approaches infinity, this value here approaches 0. Okay, so that's your hint. Also, if you need a second hint, if not, go ahead and use that hint and try this problem. But here's your second hint. If you have values in the top and the bottom, so let's say you have like 9x over 2x, something like this, plus, doesn't matter. Here's the key. It doesn't matter what's over here. When you're finding these asymptotes, you're finding what's called, in a sense, the end behavior, because you don't care what it's doing in the middle of the graph. You just want to know what's doing way the heck out to the right and way the heck out to the left. In this case, it's positive infinity, so it's way the heck out to the right. When you plug positive infinity in there, you notice the top and bottom are growing at the same rate. And also this, if you take just the leading coefficients, simplifies down to 9/2, and so then that's the limit. So 9 times infinity over 2 times infinity is just 9/2. And then that, oops, not x, y. That is your horizontal asymptote. So there's your hint. Now go ahead and try this one on your own. Okay, here I have in black, when you plug positive infinity in, you'd have 2 over infinity, which is equivalent to 1. So 2 over infinity is equivalent, 2 over infinity is equivalent to 0 plus 1. And then 5 times infinity squared minus 1 infinity over infinity squared. But here, remember, the rest of this minus 1, doesn't matter what that is. Get rid of it. So just look at the 5 times infinity squared over the infinity squared. And remember, the infinity squareds, in a sense, cancel each other out. They grow at the same rate. So you would just have the 5 over 1. So you'd have, in this case, 1 times 5 over 1. Your limit's just 5. Go ahead and try that with the negative infinity if you haven't already, then come back to the video. When you plug negative infinity in there, you'd have 2 over negative infinity, which again is 0. So 0 is neither positive nor negative, so that doesn't matter. So you'd have 0 plus 1. And the negative infinity part is important. Very important, because that tells you if it goes to positive or negative infinity in terms of the y value. So here, when you square negative, it becomes positive. So again, both of these are going to be positive, so you would have positive 5. So the limit as x approaches negative infinity is 5, and as it approaches positive infinity is 5. And so your horizontal asymptote is at y equals 5, all the way across. And you can look at the graph of the function. I think I have a graph here. Yeah, here's the graph of the function. You can look at it easier here. As it approaches negative infinity, it approaches y equals 5. As it approaches positive infinity, it approaches y equals 5. And again, practice using your tables on your graphing calculator so you're really comfortable, know how to plug large values and small values. If you don't know how to do that, just write a note on in your notes saying, ask Fawcett how to do this, come into class, ask me, and I'll show you. It's really easy. You just have to know what to do. So talking a little bit more about end behavior models, that's basically what we've been doing. What's happening to the function as it goes all the way to the right towards infinity or all the way to the left towards infinity, and you're basically trying to find a model that, or like I should say, an expression that models the behavior of that graph. So a right end behavior model, if you look here, right end behavior model for your function, G is a right end behavior model for the function if when you take f and divide it by g is equal to 1. That means they have to be equivalent. Same thing here. G and f have to be equivalent for g to be a left end behavior model for that. So I have a couple examples that aren't necessarily in your notes. Oops, there we go. So you're going to have to jot these down just for end behavior models, because end behavior models can also be represented by leading coefficients or the highest degree coefficients if it's in standard form. Sometimes it's a horizontal asymptote, sometimes it's not. It just really depends, and we're going to do one of each. So in the first example, what I want you to do is find an end behavior model. And so your function is going to be 3x to the third minus 2x to the fourth plus 2x minus 1, something like this. Now remember, with the end behavior model, it's represented because the highest term, or the leading term, the highest, what am I trying to say here? If you put this in standard form, it's the highest term, the leading term, and in this case it's not in standard form, but the negative 2x to the fourth has the highest degree. Okay, so the highest degree term of the polynomial, that's what dictates what it's going to do as it gets larger and larger and larger, or smaller and smaller and smaller, either more positive or more negative. That's what it's going to determine. And so then your end behavior model in this case is negative 2x to the fourth. That is your end behavior model. Another example, a little bit different example. Again, find the end behavior model. Here's your function. Now you have a polynomial. You have f of x and g of x. So 9x to the third over 3x plus 9, just making this stuff up. Now, when you have a polynomial, your end behavior is determined again by your highest degree terms in the numerator and the denominator. So you'd highlight your highest degree term in the numerator and your highest degree term in your denominator. Okay? And what you're doing is you're going to set that as a limit. It's the limit. Oh, no, this isn't a limit. It's just in behavior model. So the end behavior model is those leading terms, simplify them, and that gives you just 3x squared. So if you graphed this original function, if you graph this, okay, all the way out towards infinity, it's going to mimic 3x squared. That's what it's going to look like. So if you graph them on the same graph and then went all the way out to positive, negative infinity, it's going to mimic this 3x squared graph. That's why it's called an in-behavior model, all the way out there at the end. Okay, so anyway, so in this section, you know what an in-behavior model, how to define vertical and horizontal asymptotes in terms of limits. That's extremely important. Make sure you can do that. Okay, definitely put those definitions for horizontal and vertical asymptotes in terms of the limit. Maybe write your own little definition in your own words. What makes sense to you? Put that in your toolkit. And then come to class. Let me know if you have any questions over any of this.